Good morning, all of you. Let me first thank the International Center for Theoretical Studies for inviting me to give this lecture. I'm not sure I'm really qualified to give this lecture. And let me say that it's a great pleasure after about 2 years to be in front of a live audience. I've been giving webinars for the last 2 years, not very satisfactory in front of a virtual audience. So it's good to have a live audience. And I would not mind any interruption by any of you during this talk, because in spite of giving many popular lectures, it's possible that I'll slip into jargon now and then. The risk is always there. Okay? So please feel to stop me. And this lecture may turn out to be very elementary, because I was not sure the kind of audience that'll be there. I'm sure some of you are quite knowledgeable on this subject. And so I kept it very elementary. So if some of you get bored, now the title of this talk would not have been even thought about 150 years ago, because from about 10,000 years ago to just before just after 1850, there was a period of very stable climate of the Earth. And as far as we know, within the accuracy of measurement, that the global mean temperature didn't fluctuate more than half a degree or maybe 1 degree. Okay? So in this period, the human civilization, agriculture really thrived. Agriculture demands very uniform temperature, and the human population exploded. So in our culture, in our attitude, we assume that Earth's climate will be stable. And only now, we in the last 50, 60 years of research and discoveries, we know that Earth's climate was not always this stable. And now that we are perturbing this climate through our actions, we have to be ready for consequences which we had not foreseen earlier. So that is the whole point on this lecture. Now, I've been giving lectures for 35 years on climate change, and very often, even in my own institute, there are a lot of people who are climate skeptics. That is, these are the people who think, yeah, climate change may be there, but it's not a serious issue. There are other more important priorities. And the best example of this here is right in front of us is the famous naturalist David Attenborough. All of you have heard him so many times. Up to 10 years back, he was skeptical. Okay? And I was really surprised. Here is a man who has gone all over the world, looked at how biodiversity is being destroyed, what human beings are doing to the biosphere. He did not believe that human beings are altering Earth's climate. And this is because the feeling is that, yes, human beings have altered the landscape, agriculture changed the landscape, but it's all regional. It is difficult to believe that we can alter the global climate. And that's partly understandable, because 71% of the Earth is ocean. And we believe we're not doing much ocean, although we're doing a lot, we think we're not doing much. We have, of course, mainly altered the land, primarily. Okay? So Attenborough probably thought, why cry wolf? Maybe it's not happening. But in the last 10 years, he really got convinced. And in the recent years, he has made a lot of pleas about controlling climate change. Now, all of you, I'm sure, got interested in this topic last year when the Nobel Committee in Physics decided to award Nobel Prize to Hasselmann and Manabe for their work on understanding climate. And interestingly, Parisi's work is for complex systems, which is the main theme for ICTS. But he also contributed one paper on related to climate change. I'll just say a few words about that. Now, Manabe's major contribution started in the 60s, when the computer power that was available was so small, is smaller than what is in the mobile. Okay? But he had a very great imagination and ability to model. So one of the first models on the impact of increasing carbon dioxide was just a single layer model in the vertical, that's all. And he was able to show that if you double carbon dioxide, the temperature in the lowest layer of the atmosphere, from surface to about 100 millibar, temperature will go up. But as you go above into the stratosphere, the temperature goes down. Okay? This was a result which surprised many people. It was counterintuitive. And he pointed out that why this happens. And the interesting part about that is Hasselmann immediately understood the importance of the result, because at the time when Manabe discussed the result, many people had doubts whether human beings are having important climate. Many people, especially astronomers and astrophysicists, told us, yeah, sun influences climate. How do you know that sun is output is not changing and it's warming? Okay, this was a proof that it is not due to sun, because if sun was heating Earth's climate, it will heat both the troposphere and the stratosphere. It is the greenhouse gases have an opposite effect, and I will not give the result why. You can think about it. It's a very interesting puzzle. Why the same gas in the troposphere warms the Earth but cools the stratosphere. Okay, and so Hasselmann made a strong case that since the discovery of Manabe, it should be possible to detect the human impact on climate by looking at the opposite impact of CO2 increase in the troposphere and stratosphere, and that signal was seen in a few years later. Now the impact, the work of Parisi, although mainly in complex systems, he wrote one paper 40 years ago, 1982, on stochastic resonance. Okay, and this paper always puzzled me, because having been trained in mechanical engineering in what I would call deterministic systems, my idea of resonance was a system like a simple pendulum being forced by external force, and the resonance occurring because of the match between the forcing frequency and the natural frequency. That's my understanding. Here they were saying that resonance in the climate system was driven by stochastic processes. So very interesting thing. I'll say a few words about it near the end of the lecture. Now, before I go further, I want to make sure that there is no confusion about whether climate variability and climate change. I'm sure most of you know about it, but I want to make sure that I am able to clarify this. This is what all of us experience every day. So we know, all of us understand this because it affects what we wear and what we do. This is also known to many people, especially I find in India, and I talk to farmers, they are much more aware of climate variability because they are out in the field all the time looking at changes year to year. People in urban areas are somewhat insulated from this fact. You live in air-conditioned rooms or well-controlled environment, you will not understand this part. And this is a part we are now concerned about. Now, every year around March, when the temperature of Bangalore starts going up, I get lots of queries from especially news media about global warming. Because around March, the temperature starts going up on certain days. But as all of you know, this is just climate weather variation. Weather fluctuations are quite common around this month when the transition occurs from winter to summer. This is not anything to do with climate change or global warming. So the weather is really concerned with regional, atmosphere, and local scales from hours to days. But climate is concerned with things that are much longer time scale. It used to be considered as 30 years and above. Now it has views have changed. When I read about it in my undergraduate days, climate was 30-year mean of the weather statistics. But now it's even year and longer considered as climate. And the scales change from regional to much more global in character, because many things affect the statistics of weather. And the main point is atmosphere, ocean, land, and humans influence climate. Well, this is mainly atmosphere. Now, to make this even more obvious, maybe too simple, but just for your reference, I've lived both in Bangalore and Chennai. So I've shown you here the distribution of maximum temperature in the month of June here, over Bangalore and over Chennai, okay? And of course, all of you know that Chennai is warmer than Bangalore on most days, but there are days when the temperature of Bangalore can be above that of Chennai. Those are weather. There are certain days, especially in March, April, you start looking at your on your weather forecast, you will see that a certain day in March, we are actually warmer than Chennai. That can happen, but the distribution is clearly quite different. Bangalore on average is about 6 degrees colder than Chennai. And today, because of climate change, both these distributions are shifting to the right. And that's why you're getting extreme events. Okay? As a matter of fact, the fact that extreme events go up was known a long time ago, you don't look at a model. It's just realization that this distribution has a shift. If there's a mean 1 degree increase in temperature, the whole thing shifts to the right, and you start getting more and more extreme events in any city. Okay. So let me just summarize this whole point, that weather is on a very short time scale. Then you go to climate variation from years to weeks, years to decades to centuries and longer. And climate change is a word generally used for a very large or a step change in climate variability. Climate variability is natural changes that occur in Earth's climate going from decades to centuries, but sometimes the changes occur more rapidly. Okay? How rapid is a matter of subjective judgment there, you'll see that. So climate change comes into play. It can be both natural and it can also be anthropogenic. But today, unfortunately, when you use the word climate change, we mean anthropogenic. Unfortunately, that has become common, but climate change has occurred in the past due to natural causes. Now, one example I want to give you, maybe a little too early, but I'll tell you just for interest here. This is data taken from ocean sediments about the amount of dust from rivers going into the Atlantic Ocean. And based on that, it was discovered that the amount of dust going into the Atlantic Ocean from Sahara between 10,000 years ago and 5,000 years ago was much lower than what's happening today in the last few thousand years. And the change occurred rather sharply. Okay? This was called the Green Sahara. When Sahara was green, there are lots of evidence towards that. And Sahara is now completely desert. And this was a very important discovery because a lot of people assumed that Sahara had become a desert because of human impact. But this occurred a long time ago. It's difficult to argue that humans had an impact. And so this is now believed to be due to natural factor, this transition. But notice that it occurs rather rapidly. Of course, in human time scale, it may not look rapid because this is thousands of years here. But still, it gives a clear indication that rapid climate change can occur occasionally, not always. Now, we come back to the 20th century. We are seeing a lot of years which are setting world records in global mean temperature. But notice that it's not happening monotonically. Although today the carbon dioxide level is the highest that has ever been in the last million years, last year's temperature was not the highest. That's because of natural variability climate is interacting with human-induced climate. So that's why it is very difficult sometimes to convince people who are not in the field whether the change we are seeing is natural or anthropogenic, because it's a combination. Now, if you plot the global mean temperature, here it is in blue, and carbon dioxide, which is the main culprit here, you see that carbon dioxide change is somewhat uniform and smooth, while the global mean temperature fluctuates a lot. And so this has caused a lot of confusion among politicians and others, saying that, really, maybe these two are not connected. Maybe the correlation we see here is purely a chance. Okay? And especially this particular event in the 40s and 50s raised a lot of issues when I used to give talk as to why the temperature is falling when CO2 is increasing. Now, it's important to highlight to people that when we talk about anthropogenic climate change, we are not talking about year-to-year changes. We are talking about long term. In the long term, from let's say 1900 to 2000, this change is definitely change in temperature is related to CO2, although year-to-year need not be. Year-to-year changes are due to natural variability of the Earth system, because remember that most of the heat that is trapped by carbon dioxide is stored in the ocean. And that ocean exchanges heat with the atmosphere. And that occurs sporadically and in a nonlinear way. So temperature changes year to year will not follow exactly increase in CO2. So this particular event, for example, that occurred in 1940s, even today there's no explanation which satisfies everyone. But one explanation is due to the changes in the Atlantic Ocean, the cooling that occurred in that period. There are others who believe this is due to changes in aerosols, about which we'll hear more tomorrow. Now, you can see that the Atlantic Ocean temperature did go down during this period. And so that, especially this is, I think I'm missing some part here. Yeah, this is the Northern Atlantic, this is near the tropics. And Northern Atlantic showed a cooling during this period due to natural causes. Now, in order to understand climate change in a good way, let's start with a simple climate model, and in which we look at the global mean absorption of solar radiation by the Earth atmosphere system and the emission to space for the various functions of temperature. And as most of you know, the emission from the Earth's surface is trapped by these important minor gases: carbon dioxide, water vapor, methane, and ozone. And so that controls the amount of radiation can be lost to space. And this was known, of course, a long time back. As a matter of fact, Fourier was the first person to suspect that the Earth's atmosphere must be trapping the emission, although at the time when Fourier proposed this, we did not have accurate data on the absorption spectrum of CO2. So not that. Still, he had a good intuition that Earth could not have been this warm, but for trapping of the radiation by the atmosphere. Now, little later, Arrhenius, the famous chemist, he was able to get some data on carbon dioxide absorption spectrum, and he actually estimated how much the temperature of the Earth will increase due to doubling CO2, and his estimate was quite good for a time when the data that he had was so limited. Okay? Later, engineer called Callender in England, who was dealing with steam power plants and so on, he got more accurate data on carbon dioxide emissivity and absorptivity, and he also made an estimate which was a little more accurate than Arrhenius. But the most interesting thing is, all these people were in colder climates, and they all thought an increase in carbon dioxide would be beneficial to human beings. So they all did not think it's a serious issue. They were quite happy that England and Europe will be warmer and good for agriculture. Remember that. So our views have changed in the last 100 years. Now, today, because we have satellites and a lot more observation than what Fourier and others had, we can actually quantify the greenhouse effect. Okay? And it's a number which is worth remembering. Today, the Earth's surface emits about around 390 watts per meter squared. And we know from satellite that this is the emission that goes out actually. So 150 watts per meter squared is trapped because of the atmosphere. So that's a round number to remember, and it's going up slowly because of CO2 increase. Now compare that with Venus. Venus surface temperature is very, very high, okay, much higher than Earth, and so it emits much more radiation. And its emission to space is comparable, interestingly. And so the greenhouse effect is about 100 times larger. Now, why I'm pointing this out is if you talk to people who look at the origin of the solar system, they point out that Venus and Earth are called twins. They have a similar size, similar mass, similar beginning, similar composition of the atmosphere. Everything was similar. And for some reason, Venus went into a very warm climate, unlivable climate. Well, Earth, one reason we all thought, everybody thought, that's because of the distance. Venus is closer to the sun than the Earth. But that is not the full story, because although Venus towards the sun is completely covered with clouds, and hence its reflectivity is much larger than Earth. And so that alone doesn't explain it. And the only explanation is the amount of carbon dioxide that is there in Venus. Ironically, if you look at the total amount of CO2 in Venus and Earth, including both what is in the surface and the atmosphere, is almost same. It's an estimate. Nobody has actually made measurement in Venus. But interestingly, in Venus, all the CO2 is in the atmosphere. On Earth, all the CO2 is in the ocean and as calcium carbonate in rocks. It's just the fact that we are lucky that all of our CO2 is trapped mostly in the surface and ocean. Now, this was warning Carl Sagan gave more than 30, 40 years ago, that if we're a little careless, we can go to the conditions of Venus. Now, if you look at the amount of trapping of radiation that's done by the different gases, water vapor is a dominant gas in terms of ability to trap Earth's radiation. CO2 comes next, and then of course ozone and methane. And this caused a lot of confusion among the lay public, because they think if water vapor is the dominant trapper of radiation, why are we not controlling it? So this one, in IPC, very often you have to talk to many people and tell them that water vapor is something we cannot control. The laws of thermodynamics dictate how much water vapor will remain on the atmosphere, depending on temperature. So ironically, although this is not the dominant greenhouse gas, this is what controls Earth's climate. Now, this was not known till very recently, that CO2 is the, what I would like to use as an analogy with ecology, keystone species. Ecology, that the keystone species controls the whole ecosystem. CO2 plays a role on Earth, which was not realized for a long time. Okay. Now, so global mean temperature is controlled mainly by carbon dioxide, with water vapor acting as an amplifier because of its dependence on temperature. Now, the other thing water vapor does is remarkable, because when it condenses as a liquid and forms clouds, it reflects radiation, and it becomes ice, of course, it reflects a lot more. So the difference is very enormous. If you look at this iceberg and the ocean barely reflects 10%. This reflects 90%. So when you allow this to melt, you are increasing the amount of radiation that is being absorbed almost 9 times. Okay? So that's a big change people didn't quite appreciate. So water vapor, when it condenses into liquid or ice, it controls the Earth's climate by controlling the reflection of the Earth's surface and atmosphere. So we can write this down in a very simple equation, a balance between incoming radiation. This is called the solar constant, and has been measured accurately now with satellites. And so because of the surface area of the Earth being 4 times the cross-sectional area, you get this S by 4 here, into 1 minus reflection by the Earth atmosphere system, and this emission a function of temperature and greenhouse gas. Okay. And of course, the reflection is called albedo by astronomers, and we continue to use that same term. Now, this is a curve which I find very convenient to start with. So the emission of the Earth depends on temperature, that's the dotted line. And the absorption has a much more complicated variation because of the amount of ice on Earth. If there's no ice on Earth, you will get very low absorption of sun's radiation. I'm sorry, if there is a lot of ice on Earth, you get almost no absorption, very low absorption, you get only 100 watts. But at the present climate, you're absorbing around 240 watts a meter square. Okay. In between, there is another condition where we little more ice coverage. So what it shows is that under the present value of the solar constant, with 365 watts a meter square, accurately measured by satellites, there are 3 possible solutions. All are valid solutions to Earth's climate. And from whatever data we have had over the last 1,500 years, we know these 2 states do exist. This is our present climate, 15 degrees centigrade, and about 10 degrees centigrade during the last ice age, 20,000 years ago. Okay. This was a bit of a surprise. This is called the snowball Earth, when as it is completely covered with ice and snow. And when the Russian climatologist Budyoko, who first wrote this model, he was not too sure whether this will really exist. Because the feeling was that if the Earth is completely covered with ice, then no life can survive. So people thought it's not possible. But recently, some new evidence emerged that it had happened. So the key point is that from that simple model, we can say that it is possible for the Earth's climate to oscillate between extreme states, completely ice covered, completely ice free, and in between. And evidence today shows it has happened in the past. So from that perspective, we have to be cautious about the stability of the Earth's climate. If it has oscillated over a long period, of course, millions of years, it can happen again. Now, the fact that Earth was once completely ice covered was not believed for a long time because evidence was not there. And so only one person, Paul Hoffman, went around the world looking for geological evidence to show that there were ice up to the equator. Okay, and it's a very interesting story. I don't have time today to talk about it. It's a very interesting story. I want all of you to read this book. This is a popular book written by Gabriela Walker. Very nice story. The interesting personalities and clashes and debates and priorities and so on. So I suggest all of you read it. It's a wonderful book to read. He had a very interesting personality, this man. And finally, he has been proved right. Initially, no one believed that it can happen. Now, majority of the people agree that such a thing did exist in the past. And when was that? That happened a long time ago, 600 to 800 million years ago. It is believed that with evidence we have, that from pole to pole, there was snow and ice, okay? In other times, of course, Earth was partially ice covered, but this was a period when it was almost completely ice covered. Now, the question we had asked is, why did it happen so long time back? Why not in the recent past? Now, that is to do with the way sun behaves like a star. The sun's emission has been increasing as the nuclear reactions are getting more and more active. From the beginning, at the beginning, it was only 70% of today's emission. So what is that today? Okay. And if you look at about 1 billion years ago, approximately, it was around 5 to 7% below the present value. And if you look at the simple model I propose, one can show that it requires only a 5 to 10% decline in sun's output for the Earth to move into an ice age. Okay? And that was very surprising when it was first discovered, but now we know that, yes, that is possible. And this happened also at a time when the Earth's continents were all around the equator. That's another complication. So I won't talk about it. You can read about it in some of these books, how not only the sun's radiation input, also the orientation and the location of continents also plays a role in Earth's climate. That's not relevant to us today because our continents now are not shifting. Okay. Now, although all the evidence from simple models were there, people still had doubts because simple models are nice to teach in a class, in a popular lecture, but one has doubt whether the answer is dependent on the model you construct. So today, fortunately, because of the advent of complex climate models, about which we'll hear a lot in this workshop, so people have run models involving both the atmosphere and the ocean as well as the land. These coupled models have been now very used by lots of centers in the world, and it has been used to understand this issue. Okay, and they use standard laws of physics. These are all well known to all of you. I will not talk about it, and anyway, others will elaborate on this in this workshop. Now, what do these models show? These models show that if you maintain the carbon dioxide concentration at 280 parts per million that was there in 1850, this is what we'll get. The variation by various, there are many simulations here, not one, hundreds of them, okay? And there are about 36 models which have been used here. So you can see that the Earth temperature would not have changed much in the last 200 years here if CO2 was constant. The black is the observation of global mean temperature, and the red is a model in which you allow CO2 to increase as per the observed value. And it clearly shows that after 1970, one can say with quite a lot of confidence that the increase in temperature we have been seeing is primarily on account of increase in carbon dioxide, because the model does not show that increase when you keep it constant. So this is the power of modern computer modeling. Now, in addition, Manabe, who got the Nobel Prize, he also showed long time ago that it is not carbon dioxide alone, but water vapor also played a role, because in the model he fixed water vapor concentration in the atmosphere and showed that the temperature increased only 1 degree due to the doubling of CO2. But if you allowed water vapor to increase, it went up to 3 degrees here, almost 4 degrees here in this model. Okay? So the point he made was that CO2 was the main trigger, but the actual increase in temperature was primarily due to water vapor contributed most of it here. Okay. So this was an important result to demonstrate that there are lots of other changes in the Earth's atmosphere which add on to the initial trigger by CO2. Now, these models have been used to do many experiments which are very, very illuminating. I like it very much. So in this model, I think the reference missing here is up there. So White and others ran a model in which they did various things. First thing, they reduced the incoming radiation by 6%. This is total solar irradiance, 6% below normal. Then the sea ice amount increased very slowly from 10% to around 25% over 1,000 years. So this is not interesting. But instead of 6%, it increased by 9%. You see the change. It reaches 100% sea ice cover by 600 years. And if we increase it even more, it occurs earlier. So clearly, reducing solar radiance by 10 to 15% has a huge impact in a matter of few hundred years. But the one I want to show, the most interesting thing is, if we remove all the CO2 completely, the Earth becomes ice covered by just 300 years. Okay. So this is a point that is worth understanding. Although the concentration of CO2 150 years ago was only 280 parts per million, and one would have thought it's very minor, not worth it. You remove it, the Earth becomes ice covered. So that shows the dominant role CO2 plays in Earth's climate. But here also remember, water played a role. CO2, you remove, the Earth starts cooling, water vapor starts falling. Here also, water vapor played a role of an amplifier to amplify the cooling. Okay. Yeah. Now, one more example. I think this came. Yeah. One more example I want to give is the role of volcanic eruption. Some of it may be again be mentioned tomorrow. Volcanic eruption has influenced Earth's climate for a long period, but normally volcanoes erupt for a short time. They cool the Earth for a few years, and now after these aerosols settle down, they go back. So this is again an simulation by a model in which after an eruption, the temperature fell by around half a degree. This is typical. This is simulating the eruption of Pinatubo in June 1991, about which you have a lot of good data. But what I want to show here is again, if you did not allow water vapor to change in the model, only the aerosol to cool, it will only cool by around 0.4 degrees. Here also, water vapor played a role by reducing its amount during cooling and increasing the cooling rate. Now, all the information can be put down in terms of the relative role played by incoming solar radiation, not dimensionalized to the present value, and the amount of CO2. You can see the various possibilities here in this graph. And it shows both two branches, the ice-free branch and the ice-covered branch, and in between a solution which are stable and unstable. And what this shows clearly that if you reduce, in this model, reduce the solar constant by around 5% in this model, you can shift to the unstable branch here. And at the same time, if you reduce the solar constant by 25%, but increase the CO2 to much larger than here, you can maintain Earth which is not completely ice covered. Now, this is very important because this was a major paradox for a long time. Astronomers knew that sun's output was very low in the beginning. So the question was, why was not Earth completely ice covered at that time? And the argument is that at that time, the concentration of CO2 on Earth was much, much higher than today. Percentage-wise, it was 96%, but actual amount we really don't know. That is a long time back. But the feeling is that at that time, CO2 was sufficiently high in the Earth's atmosphere that in spite of the low incoming radiation, it was able to maintain an ice-free Earth. Now, of course, today we are in a different world. We have allowed the CO2 to increase from 280 parts per million. That was almost steady for about thousands of years. And the last 100 years, you let it go up. Now it has crossed this one to 400 parts per million. Okay? And last month, 2 months back, it was 415. Now, remember that CO2 is an important player in Earth's climate, and it controlled Earth's climate for a long period before human beings came into play. And this was done by this cycle of volcanism and weathering. Volcano release CO2 and weathering remove CO2. And what's interesting is that whatever data we have today, we know that the amount of CO2 that is released by volcano per year on an average, and amount that is removed weathering is around 0.03 gigaton per year. And this is much, much lower than what human beings are doing. This is something I find many people find it difficult to believe, that human beings are contributing to the CO2 emission, which is 100 times more than what volcanoes do. Okay? So this is a fact, but for a long time, volcanoes had an effect on Earth's climate on a long time scale. So the key point I want you to remember at this point is that the global temperature that is rising now due to our action is 10 times faster than what we have known happened in the past. I'll use my examples soon. Carbon dioxide also is increasing at a rate much faster than what happened in an abrupt climate change about 15,000 years ago. So both CO2 and temperature are rising at a rate much, much faster than we have experienced. To me, that is something which is not highlighted by many people, because when they say that temperature to 1 degree, a lot of people tell me, geologists tell me, oh, it happened in the past, so what's the big deal? Why you worry about it? Same thing about CO2. CO2 has been very high in the past, long time back. That's not the issue. The issue is the rate of change. So this is a point I'll come near the end, that the rate of change is what we have to worry about, not the change itself. The change itself may have occurred in the past many times. But as far as we know, the rate of change has never happened at this rate. Now, I want to go back to the past, because if you want to predict future climate, you better know or understand what happened in the past. So let's see whether we can understand whatever climate change occurred in the past. And we are lucky that in the past 50 years, people have been able to figure out how the Earth's climate changed in the last almost million years. Okay? But of course, this is a very indirect evidence. There was no thermometer before 1700. So all the evidence is proxy. I never believed in it, frankly. I always thought, how can you take some other property of a species and then predict temperature? But I can tell you today, the amount of amazing work done by people who look at proxy evidence, we know from not a single evidence, but from a variety of different evidences that climate change has occurred on a variety of scales. Okay, so today the confidence in proxy evidence has gone up because the evidence is coming from various sources, not one. Now, the problem is that we are mostly concerned with time scales of the order of 10 to 100 years as far as human-induced climate change is concerned. But when you go to the past, you see changes occurring over thousands and millions of years time scale. So there are different time scales, but still it's good we understand what mechanisms govern these phenomena, so that if our models are able to reproduce this, our hope is that it will also be able to predict the future. Now, this is an interesting graph I saw recently. I will not go into detail. Only want to point out that there are people inventing new terms which make life harder. Somebody calls it macro weather, macro climate. So trying to define climate in terms of the spatial scale. But it's a very interesting graph. It came out only last year, this review. I want you to look at it if you are interested. Now I'll go to the proxy evidence. The proxy evidence comes from a variety of sources, starting from, of course, we had instrumental data for about 200, 300 years. Written historical evidence is there, of course. And the first proxy evidence really is the tree ring. The growth of tree depends on temperature in the mid-latitudes. And of course, ice core gave us a lot of data going back to 10,000, 20,000 years. Then lake sediments, depending on the amount of sediments, can go back very back in time. Coral reefs tell a lot because they're sensitive to temperature, they tell a lot of temperature. But the most important evidence came from ocean sediments and coastal sediments, which go long back, almost 100 million years. Okay. So any one evidence I won't trust because there could be other factors. But when you bring in a variety of different evidence together and they show the same direction of change, we can trust it. So this is the first one, which is the most recent past from tree rings. And this was the data which was put out by Mann, Bradley, and Hughes, which created huge controversy on how many we heard about it. They were able to show, based on mainly the mid-latitude tree data, that the temperature was slowly declining over the last 1,000 years, and then during the last 150 years, it went up rapidly. Okay. Now, this particular graph is called the hockey stick. Looks like a hockey stick. Okay, and created huge controversy because this is proxy evidence, and this person, Michael Mann, is an amazing person. He's a statistical climatologist. So he had to look at the evidence from various trees from all over mid-latitude and carefully construct this one. There are problems with this kind of reconstruction. But if you go through the paper and if you have a subject domain expertise, you understand that he has done a good job. But many outsiders jumped into this and said this all, he actually they said he manipulated the evidence. Okay. And you won't believe it, he was in the University of Virginia and he was essentially driven out. He experienced what Galileo experienced many hundred years ago. So he ultimately went to Penn State, which is a well-known university, of course. But later on, others did the same work and confirmed what he did. And now we know that this data, in spite of all this noise, a lot of noise in the data, it clearly shows that climate is fairly stable for about 1,000 years before it started increasing rapidly. So this is a different data set showing the same kinds of evidence. I'll tell you why the people who wanted to attack this were mainly funded by the fossil fuel industry. And they wanted to argue that there is enough noise in the data, the temperature had gone up to 0.5, 0.6. And at the time when they argued, we were somewhere here. And they said, you know, this is comparable to this, so there is no proof of human. So this had a big impact on IPCC process because you had to deal with these deniers all the time. So again, I don't have time, so I want you to read two books. One written by denier, who has really no background in science, and who wrote this book about illusion of hockey stick, and then the response from Michael Mann, who shows how he had to deal with this attack on his scientific integrity. Okay, now we come to a much longer time scale, the ice ages. This is the most interesting event because temperature changed a lot more than in the last 1,000 years. And only about 100, 120 years ago, in the late 19th century, people realized that in the Alps, some of the regions where the rocks had striations, that these were caused by glaciers. So they realized glaciers had come much further down than at that time. So then interest in ice ages became very huge. And then came Milankovitch. I don't know whether I can do anything about, can you bring it on lightly here? Because it's slightly, upper part can come down. Here I can see it, but no, I cannot see it there. Okay, so Milankovitch was interestingly trained as a civil engineer, but he took interest in climate, and he argued that the changes of the Earth orbit around the sun, the three changes all of you are aware of, change in eccentricity, changes in Earth's tilt, and the precision where it's pointing. All the three contributed to a variation in the amount of radiation falling in the polar regions. And if the amount of radiation in the polar region during summer was below average, then the snow has to accumulate and the ice age starts growing. That was the theory. And yeah, it's okay. Thank you. So, so he proposed this theory in 1921, almost 100 years ago, but nobody believed him because people couldn't believe that small changes in the Earth orbit can have a huge impact on Earth's climate. And partly because at that time, the role of water vapor, the role of melting of ice, not fully understood. So Milankovitch had a great difficulty in convincing people that ice ages are caused primarily by the trigger induced by changes in Earth orbit. He made all this very nice calculation. Remember, this was a time before slide rules and calculation, all done by hand. So I'm really impressed by this commitment that he calculated everything by hand and showed that about 125,000 years ago, when we had a warm period, before that we had a cold period, the amount of radiation falling in the northern polar region had changed from -50 to plus 30, 40. Okay? And he said this change over many years, not 1 or 2 years, thousands of years will cause the ice to accumulate. And in this case, the ice actually melted. Here the ice accumulated, and the next 10,000 years, as the radiation went up, the ice melted. Okay. Now his bad luck was that there was not enough observational evidence to support his hypothesis. So by the time he died, people had not really accepted that hypothesis. But in the 1960s, a remarkable scientific experiment undertaken in Antarctica, in a place called Lake Vostok, where scientists and engineers went all the way to drill almost 4 kilometers of ice and to look at the air trapped in the ice and to look at the isotopes of water in the ice to deduce temperature. This is a remarkable achievement, and some ice cores can be dated annually because you can see the clear layers. Some of them we have to do it through other methods. So this is the ice core, and as the snow falls and compacts, this air that is trapped is sealed forever for millions of years. So that's the advantage. As long as you're able to get this trapped air in the ice in the laboratory and carefully take it out without contamination, you know what are the composition of the atmosphere at that time. So that is the this portion not useful. This portion is what is useful. And how do we deduce temperature? This is a method based on isotopes, and the argument is that when the water evaporates from the ocean, only there is a preferential evaporation of 16 compared to 18, and that change keeps happening until it reaches and falls on the polar regions. Okay, depletion occurs. So from the amount of depletion of O18 in ice, you can deduce. Now there are a lot of controversies about this proxy method, but I would say the most reliable one is the fact that if a lot of this water evaporated and became ice, then surely the amount of depletion of O18 is a measure of the amount of ice that occurred at that time. That's very clear. There's no problem about that. Pure mass balance tells you that more ice must have occurred there if the O18 is depleted. But the related temperature is a little more complicated. But there is evidence from, anyway, these are, you'll see a lot of graphs showing delta O18. It is the sample 18 quantity minus standard given to everyone and multiplied by 1,000 because the numbers are changing a little. So this is per 1,000, okay? Now this is talk about, there's no controversy on this one, that the time series of delta O18 is exactly the same as time to ice volume because just as a question of where the water is. But it can also be related to local temperature because today if you measure the delta O18 in any stations all the way from polar to tropical stations, you'll find that there's a connection. But this is local temperature, this is not global temperature. Okay, other thing is that There's a connection between what's happening in Antarctica and what's happening in the equator. Equator is this region, West Pacific, very warm part of the Earth. If you look at the proxy data from ocean cores here and ice cores here, they're very well connected. Okay. So changes, when they occur globally, they connect the tropics and the polar regions. Now, this is the ice core about which I'm going to talk about, that air in the ice core. That's what gave the real confidence about the role of CO2. Now, this is the data which I think is the most important data we have got in the last 50 years. It compares the concentration of CO2 in blue and the temperature in Antarctica in red. Okay, and the key point about this figure is see the high correlation between CO2 and temperature. So this clearly shows you there's a very close coupling of the Earth's temperature and carbon dioxide over the last, in this case, 400,000 years. So this evidence, when it came clearly, all the doubt people had about the role of CO2 was pretty much gone. But still, because this is such a long period data, and when you take data over such a long time scale, the error in temperature measurement is of the order of 1,000 years. You will forget that. Today you can download all the data on your computer, but remember that the time axis is not that accurate. It has an error bar. Okay? Because sometimes I've seen people happily do all kinds of manipulation of data without knowing that the time axis is not that accurate. The measurement of this delta O18 values are pretty accurate. I mean, but time is difficult to measure because either you do it by counting annually or you use some radioactive technique to find out what the temperature is. Now, this is one more graph just repeating that, showing that not only carbon dioxide, but also methane, both greenhouse gases, varied along with temperature right through the glacial integration cycles. Okay. Now, this is a full graph all the way to the present day. And the key message is that the last 800,000 years, the variation in carbon dioxide and temperature in Antarctica were going together very, very closely. And today, they are not. Today, our carbon dioxide has gone well beyond the scale, 415. Temperature has not gone more than 1 degree. That's because you must remember that when CO2 goes up, the response of the Earth system will take hundreds and thousands of years. It won't happen immediately. The ice is melting, will continue to melt for the next couple of 100 years. So we are going to see this going up. Okay, but it'll take time because ocean stores the heat and it slowly comes out and it melts the ice. So up to here, everything was following everything. And once we allowed CO2 to go up rapidly, the temperature cannot follow the same rapid change because of the inertia of the system. Now, this is the message we got from the data on ice ages, that ice ages were driven by changes in radiation in the polar region. Increased radiation caused melting of ice, temperature increased. Immediately, there were two simultaneous feedbacks, one due to greenhouse gases, the other due to changes in albedo, and both these contributed to the ice age cycle. Okay, so that was well understood, really happy. But the question that was asked about is about the periodicity of the ice ages. The key message that came out from Vostok was that there was a major ice age every 100,000 years. Okay? In this 400,000 year data, we have 4 major ice ages. Now, the point is, why is the 100,000 year cycle dominating in the ice ages? Okay, that was the main question. Now, the problem was that when people looked at ocean data, which goes back to millions of years, this is 3 million years here, there was an interesting situation. The 100,000 year cycle occurred only during the last million years. When you go back in the distant past, it had a 40,000 year cycle. This is very close to the eccentricity variation of the Earth's orbit around the sun. This is close to the variation of tilt. Okay, and so the problem was, why is this occurring here and why is this occurring here? And that issue has still not been resolved. Now, to bring it around more clearly, if you do a spectral analysis, you will see that the amount of radiation falling in the polar region can be calculated as done by Milankovitch. The major power is in the precession cycle. I will call it 20,000 for convenience. And next is tilt, and there is no power at all in the extended cycle, hardly anything. But the delta 18 data tells you that in this period, a long time back, the power is in 40,000, but in the last million years, the power is here. Now, this was a big puzzle because the so-called driving force is here at this period, and the response is something else. So all of you know about linear, nonlinear system. You may recognize that this clearly shows the system is not linear. If the system was linear, then this forcing should have caused this to be the dominant period, right? But it is not. It is either this or that. So immediately everybody tried to understand what is the cause of this nonlinearity. Yes?
The orange curve is what?
Huh?
Sorry, what is the orange curve?
Orange curve is the 100,000 year dominant periodicity in the ice volume. In the sun's radiation is not there. So if you look at, you do the first spectra of the incoming radiation, 100,000 cycle is very weak. Okay? But in the data of ice volume from delta 18, it is dominating. That is the main puzzle. Okay. That's shown again here in another graph, that in the solar input, 20,000 year dominates. In the ice core of the last million years, this one dominates. Okay. So again, I wanted to highlight this by showing the difference between the radiation data and the ice data. Ice data shows this one, and infrared data shows domination of that one. Hardly any signal here. So as soon as it became known it has to be nonlinear, everybody jumped in. Everybody knew about nonlinear system. So Salzman, I don't know how many of you know him, a very famous expert in geoscience. He was a student of Lorentz of the chaos fame. So actually his master thesis was with Lorentz on this chaotic system. And the story goes around that he and Lorentz didn't agree on some of the interpretation. So he moved on to do something else. And so he used his experience in his master's thesis to come up with a nonlinear model for the glacier mass, for the CO2 and ocean and their coupling. This only problem with this model is that it's a heuristic model. There is no, it is not derived from first principles. He just uses heuristics idea to put some nonlinear terms in the equation. And this is the forcing from the radiation. And then he put in a few nonlinear terms and connected ice mass to the carbon dioxide and temperature. And using that, he was able to show here, let me see the color schemes here. Yeah, the model is black and the observation is in color. Okay, the top is the ice and bottom is CO2. So what's very impressive about the model is that it is able to reproduce the last 4,000 years, not exactly, but broad features. Okay, so he argued that if you believe my heuristic model of nonlinear interaction, you can reproduce a 100,000 year cycle. But many people had doubts about that model, when a model is not derived from first principles. Then came a group of people who are interested in solid mechanics. They argued that if ice sheet of the order of 4 or 5 kilometers appears on land, the land sinks by about a kilometer. Okay. As a matter of fact, very interesting thing is today, parts of Sweden are still moving up after the ice melted 10,000 years ago. They're still going up because there's a time lag of many. It's not an elastic medium; it's a plastic medium. It has memory in it. Okay. So many people argued that if ice sheet appears over land, the land sinks. It will start melting the ice again because the temperature will go up. Okay. So this bedrock depression is a very important issue. So they included that in their model. Okay. So this is combining ocean atmosphere model with a solid Earth model, and they were able to reproduce the same fluctuation that the previous person did. So there are two now competing theories about how the nonlinear effects operate. One is through the Salzman's approach of nonlinear feedback between carbon dioxide temperature and ice, and the other one is due to bedrock depression. But there were other competitors here about how Earth can shift from this to the other. And the third one is what Parisi was a part of. Okay, they argued that when the Earth shifts from interglacial to glacial, it occurs when, of course, the potential function has some features, of course, that this hump is small. But it can also happen that to shift the Earth from this state to this state requires a bit of perturbation, and that perturbation can come from noise. So that was the argument, okay? And so the idea is that due to the changes in Earth overall sound, this potential function can change, and under certain conditions, this hump is quite small, and at that time, noise can play a role. Now, this kind of thinking is the argument that although the precision 20,000 cycle is the dominant frequency in the radiation, at that time it may not jump because the noise was not sufficient. The idea is that 20,000 year cycle of radiation increase occurs, but every time the Earth doesn't go to interglacial because there is not sufficient perturbation from weather noise and other noises. Okay. So, so this was the idea, and showing how depending on the potential function we can change. And it's a very nice simple model. Any student can run it. This is the rate of change of temperature. This is the inputs radiate from the sun, fluctuating at the, let's say, precision cycle. And this is the albedo, which is the function of ice and water. And this is the emitted radiation. Okay, this is a noise function. So using just changing the amplitude of the perturbation of the sun and the white noise, one can get three solutions. Here shown two of them. One is with no real perturbation, very weak perturbation here. That is, yeah, I think this is for, if I remember correctly, this is for zero noise, and this is for 0.32 noise. Okay, so so he's able to show that if you put noise, this system undergoes stochastic resonance and oscillates at a certain frequency. Otherwise, it is not going there. That's his viewpoint. Okay, you can read the paper. This paper documents various possible solutions under which he gets closer. So this is a very interesting idea that noise is the one which pushes the system to one state or other. And of course, the potential function also plays a role in that. So I'm sure many of you who have good background in this can look into it more and find out. Okay. Now I come to the last part of this lecture. This is abrupt climate change due to changes in Atlantic Meridional Ocean circulation. Now, the reason why I'm going to this now, after giving you some background in ice ages, is that what happened in ice ages is a very long-term cyclic phenomena. We're talking about 10,000, 20,000, so on. But our understanding of that has helped us a lot to have faith in our models. But now we have to talk about more time scale closer to ours. The question that everybody is asking in IPCC is whether human perturbation can cause abrupt climate change on the Earth in the next 100 years. Okay, we don't care about 1,000, 10,000, 100,000. That's all right for publishing papers and enjoying the mathematics. But real concern is, can it happen? Now, we know from the evidence of the last 20,000 years that it can happen. How did that? A lot of good data was obtained over the last 20,000 years, in the last 20 years now. So that shows that red is the Antarctic temperature, okay? Blue is the CO2 in the Earth's atmosphere, and green is the global mean temperature, okay? Yeah, green is the global mean temperature, red is Antarctic, and blue. Now, I want you to notice very carefully what is showing that by and large, the CO2 increase is very closely correlated to Antarctic temperature, okay? And it occurs before the increase in global mean temperature. To me, this is a beautiful paper by Shakun and others published 10 years ago. And I would like all of you to read the paper. It's a beautiful paper. What I like about the paper is it's just 5 pages long in Nature. but the supplementary is 50 pages long. Okay, because these people combine data from many ocean sediments and ice cores to have a combined global mean temperature data. So the referees had lots of questions about how they did it, and they answered everything perfectly. To me, this is a paper worth reading by every student who is doing research to understand how to do research and how to respond to referee comments. Okay, I would strongly recommend. It's freely available now. So this paper showed for the first time that not only that CO2 controls gas temperature, the CO2 increase occurs first and the temperature responds later. Now that is was not known in the post-doc data. Post-doc data was too crude to differentiate between CO2 and temperature. But here, in the last 20,000 years, people were able to get more data, more accuracy in time coordinate, that they were able to show. Let me explain. The red is Antarctica, CO2 is global, and this is global. Okay, yeah. So this is only for Antarctica ice core. This is combining all the data from all the data. Okay. So this shows clearly that as we came out of the last ice age, first Antarctic temperature went up, then CO2 went up. That CO2 increase caused an increase in temperature a few hundred years later, not immediately. It takes a long time. And this finally was the key point. So to me, this is the what they call, American call smoking gun. This is the evidence that CO2 is the key trigger for Earth's climate change. It occurs before the temperature change. Otherwise, in the water ice core, they were occurring simultaneously. One can only talk about association, not cause and effect. Now, I say this because I've been having arguments with a lot of my colleagues in meteorology. Whenever they see a correlation, they get excited. That correlation only is association. It's not cause and effect. For the first time, people were able to show there was a time lag between CO2 and temperature. Now the question is, why this lag occurred? That is the main part of the argument that I'm going to look at. Why did CO2 increase first in Antarctica and then temperature went up? Okay.
Antarctica data ends at 9,000.
Huh?
The data for Antarctica ends around 9,000 years.
Yes, yeah, you are right. See, whatever data they took, to get data for the last few thousand years, yeah, you're right. This is, I don't know why, the data is available, but they didn't show it here. Because I think they were more keen on showing this. This paper is all about this portion, not this portion. But the data is there. Okay. The only problem with ice core is you can't get the data of the last 100, 200 years because it's not compacted. But here we have data going back. Yeah, the others who show it all the way, at least to 1,000 years before the present.
Are you saying that the Antarctica temperature went up, then CO2 went up, then global temperature went up?
Yeah, that is the story. The story is that there is a sequence. Antarctica warms first, and that releases CO2 from the ocean, and that causes global temperature change. Okay.
Sorry, the global mean temperature so far back was obtained from the other methods.
No, let me explain to you. The global mean temperature in this paper, that's why I would recommend you download the paper. It is taken from 80 cores all around the world, not one core. Cores from Arctic, Antarctic, and all oceans in tropics and subtropics. And that's a huge amount of effort. I'm really impressed by the teamwork that goes into that. So data was taken by hundreds of scientists, not one scientist. And they were all put together. And the real challenge, I can tell you, that's where I think people do statistics and data analysis. When you want to combine data from 80 sources, you have to be very, very careful. What they call stacked. You have to stack them very carefully in time and other things. Each has its own little errors, variance, and so on. It's a very, very difficult job. That's why I want people to read the paper and the response to every comment. They have gone through every issue very carefully. Yeah, this is a remarkable paper, just published 10 years ago, I think, right? 2010, if I remember correctly. I think it's there again. Is it there? It is visible. I thought I marked it. Okay. And I'm sorry. Maybe I should send it across. Okay. Now, why did it happen? Now, the story is related to way ocean plays an important role. As a matter of fact, I didn't have time, and none of you asked any question. So if you look at the Milankovitch idea, one of the major questions they posed was, if you look at the sun's impact of Earth's orbit on the sun on the radiation in the Antarctic and Arctic, they're opposite. You can look it up, it's opposite. And so people asked, if they're opposite, it will cancel out, right? So why should ice ages occur? Because at that time, they didn't know there was a connection between the two hemispheres through the ocean. That was not known. Now we know today that whatever happens in one hemisphere, immediately the reaction is done in the next hemisphere, other hemisphere, and the two gets connected over hundreds of years, not within a short time. So this is the thing which connects the two hemispheres. The heat from the tropics is transported to the Atlantic, and there it cools and it sinks, and it goes all the way down the ocean, comes back. So this is the system which is transporting heat from one hemisphere to the other hemisphere. And this plays a very important role in modulating the Earth's climate. Okay? But this is very slow, hundreds of years, not 1 or 2 years. Now, so this is a very complicated area. As a matter of fact, I'm not expert in this. You have to call some oceanographer to talk about this. This is because the density of the ocean depends on temperature and salinity both. Okay? And so it is very subtle variation. This is called thermohaline circulation. And what complicates the matter is the surface circulation is driven by wind. Ocean surface is completely slave to the winds of the atmosphere. But in the deep ocean, it's completely thermohaline. Okay. Now, this is how we believe in the past the Atlantic mineral circulation had 3 different modes. One which is under present condition, when the air, the water sinks all the way down and goes over the Antarctic, which is colder. Then when a little colder, it doesn't go all the way down, it just has this bipodal structure. And there was a time it completely shut off. It was not there at all, okay? So there are 3 states of this circulation. And now this causes dramatic changes in Earth's climate on a decadal time scale. So this comes to more closer to our lifetime. So the circulation itself takes hundreds of years to adjust, but it can lead to sharp changes in Earth's climate on a decadal time scale. And this comes out in this, again, the same data set, but taken in Greenland. Okay, this is local, not global. And the Greenland temperature showed wild fluctuation as we came out of the last ice age. Now, I want you to remember this interesting phenomena here. I told you that in the last 10,000 years, Earth's climate was very stable. Agriculture thrived, human beings went up. But just before that, as we came out of the last ice age, the things were wildly fluctuating. Okay. So that is the other part. So there was a very difficult part coming out of the last ice age to the present interglacial. And that is the part we should not think about, because that shows Earth's climate is capable of violent fluctuation on a decadal time scale, not 1,000, 10,000. Okay. And that is coming out in many examples here of very rapid changes. Okay. Including the last rapid change, which shows changes occurring over a matter of year, I would say 5,000 year time scale. Okay. The question is, what are these changes due to? That is the main issue. Now, the major thing that happened as we came out of the last glacial is, as the Earth warmed up and the ice started melting and sinking, it had a huge effect on the density of the ocean. Okay? That's a key parameter. Okay? And to point out how, and these are catastrophic events, they won't happen slowly. Okay? And I think even today, I believe that although the modeling has gone very far in terms of its accuracy, I don't think any model can handle this kind of catastrophic changes in ice breakage and so on. And although that cartoon about the circulation was nice and simple, the reality is more complicated. Very messy feature here. Now, I just want one example just to make a point. If you take two parcels of ocean with you with the same density, but different temperature and salinity. I'll take an example, A and B. A and B have the same density, they are on the same curve, and you mix them, your density will be higher than either of these two. And again, this is very counterintuitive. You take two parcels with the same density and you mix them, you get a parcel which has a higher density and it sinks. Okay? So this is the unusual feature of thermohaline circulation. And this was pointed out more than 60 years ago by Stommel, the famous oceanographer. He made a very simple box model of the ocean between low and high altitudes. And he showed that the circulation strength in meter cube per second called the in million meter cube per second called Sverdrup after another oceanographer, that it can change in response to freshwater input due to melting of ice. Okay, and they showed that in the present state you can very soon go to a tipping point if the freshwater input is about 1/100th of the present circulation. It can suddenly reduce the circulation, and it will take a long time for you to get back to the space. But this is the point that he raised by a very simple model, which anybody can look at. And many of the people argued that tipping can occur when the amount of CO2 around 750 parts per million. Okay, this was the point that was there in IPCC also. 750 ppm looks very far away. Today we are at 415, and we are increasing CO2 at 2 ppm per year. You can say, well, it's all right, it will happen sometime, I won't be around. Okay, but unfortunately, life is not so. This is a simple model. Now let's look at what others are saying. Now, what people have done today is they have run more complicated models than two-box model. It includes all these complicated features about sea ice budget, heat transport, all that. Okay, it's all there in the paper by Stoker, who's a famous person in this area. And he is able to explain, and I strongly recommend this book. Any of you interested in getting into this field, there's a very fine book by Thomas Stoker, Introduction to Climate Modeling, available from Springer. And he showed, first thing, very interesting thing is that the temperature changes in the Arctic and Antarctic occur in the opposite direction. So when the Arctic cools, Antarctic warms. So that's called the bipolar seesaw. I don't know why you call it bipolar. So the two poles behave in a different way. And that caused a lot of surprise on many people. Why should the two poles act differently? Okay, but this model showed why. Let me see whether I can get to, yeah. So this is also modeled by Manabe, same group, Manabe got the Nobel Prize. He showed that the ocean circulation, which is fairly steady in the control simulation with no change in CO2, if you double CO2, it starts declining, and it takes about 150, 200 years to come down from about 20 to about 8 Sverdrup. But you make it 4 CO2, permanently goes to a very low state. Okay, here it recovers back for some time. Okay. So what the simple model of Stommel showed was later verified by a more complex model by Manabe and Stoker and others. Okay. Now I think I have to go back. I think I think I missed a point which I have to get back to. Now let me go back here to what to this issue now. So now that I told you that the Atlantic meridional circulation plays an important role, that had a role in this. What is the role? Role is that Antarctic warmed up first, okay, and immediately the carbon dioxide came with the ocean. And the important point about question is, why did the Antarctic warm? First question there. Now it is related to the connection with the two poles. The connection is that, let me again go back to the, let me use this as a basis. Now the point is that if the Greenland ice melts here and slows down the circulation, so if ice starts melting here and makes the water colder, and it does not, sorry, not colder, it is, because it's fresh water, it will make the ocean less saline, okay, so less dense. So it will shut down the circulation, not shut down, slow down the circulation. When this slows down the circulation, the heat transport from the Antarctic region to the Arctic will reduce. And when that happens, Antarctic will warm because heat is not being transported to the other hemisphere. So that's what happened here. So that is the key point here, that the Antarctic warming was triggered by what happened in the northern hemisphere. Okay. And once Antarctic warming occurred, CO2 went up. And once the CO2 went up, CO2 is a global gas. It goes up anywhere in the world, it will go everywhere. That is the thing which many people find difficult to believe, compared to aerosols, which are very local in character. Aerosol in Delhi is now coming to Bengaluru. But CO2 is a well-mixed gas. You can spread it across the world in a matter of few years. So CO2 released in Antarctica and then Southern Ocean ultimately spread to the whole globe and warmed the whole globe in one way. Okay. So there is a connection between the melting of ice in the Arctic and the slowing down of the Atlantic meltdown circulation and the heating of the Antarctic, and all these were connected. Okay. Now they understand this, and today, because of the detailed study of each of these events of sudden change, they're all related to changes in that circulation features. Okay, and yeah, so Thomas Tucker was able to use his model and observation to show why there was opposite response in the two hemispheres. So not once, many times in the 25,000-year period, there are many occasions when ice melted in the Arctic, slowed down the circulation, warmed the Antarctic, and the whole cycle went around. So all these, each of these lines he has drawn, is able to connect the two hemispheres, okay, through a model. Now is the most recent result. I want to have some type of questions here. So what is most interesting in the last few years, one paper published last year saying that the tipping of the overturning circulation to increase the ice melt, it depends on the rate of tipping. That's not just the amount of ice melting, rate of melting, okay? So using global model subject to freshwater forcing, we showed that the collapse of the Atlantic circulation can indeed be induced by small absolute changes in the forcing if the rate of change is fast enough. So this is a new result to me, which is very troubling. Okay, when people saw the previous model, they said, fine, some freshwater melting occurs, it happens, but we're not reached that point yet. The tipping point is far away. Okay, but now they are saying no. If you are melting ice very rapidly, then the tipping point itself shifts. Okay, now I will not say more about this. I'm hoping Professor Ashwin will next in tomorrow lecture will point out this, how the rate of change also has an effect on the tipping point. Okay, so two recent papers have clearly argued as a rate dependent process. To me, that is a point which is a new result, very new result, which must make us very concerned about the potential for rapid climate change occurring in the near future. Okay, and why should we worry about it? Because if that happens, if the Atlantic circulation actually slows down, then amazingly, due to global warming, the northern hemisphere will cool down. Okay, this is very counterintuitive result, but it will happen. Okay, so all the heat will be there in the southern hemisphere. It will not go to northern hemisphere. It will cool down. Okay? And so this is only in the first part. Okay, later on it will warm up. This is in the immediately after the stopping of the circulation. Okay, 30-year period. Later on it will change further. And why should you worry about it? Because if the Atlantic circulation slows down, one can show its immediate impact on the rainfall over Africa. Okay, these two are connected. So that's not surprising because Africa is right on the Atlantic Ocean. So whatever the Atlantic must have Africa. Okay, but unfortunately, it can also affect India. Here is a model. They show how the rainfall of India will decline due to the changes in the Atlantic. So what they do is, a model is what they call hosing experiment. They put a lot of water in the Atlantic Ocean, fresh water, and see the response of the system, and it shows the response where the rainfall over Indonesia and India also go down. Okay, so we have to worry about it because it affects the whole global climate. Okay. So these are the recent papers which have come out. Early warning signals for collapse of the, so the people are now trying to see whether they can predict this circulation weakening by looking at some variance changes in the circulation. And most recent paper says that the current Atlantic circulation is the weakest in the last 1,000 years. So already something is happening there. So this is the paper. It says after a long and relatively stable period, there was an initial weakening starting in the 19th century, followed by a second, more rapid decline in the 20th century, leading to the weakest state of AMOC in the recent decade. So this is a hint that something dramatic may happen. Okay, and so that is the one of the this is the paper which I published a little earlier. That are more even. This is an earlier one, which also appeared in Nature. Okay, showing the decline in that's beginning to occur here. It was very stable and then started declining in the here in the 21st century. So this is the comment made in Nature recently. Climate tipping points too risky to bet against. So all these days there's a tipping point is there, but it's far away into the future. We don't know. But now they're saying. Now, why I wanted to highlight this in the lecture was that we came out of the ice age to the present climate through various what do you call rapid changes in the first part of the interglacial, and then had a very stable climate. But now it's very possible that we may move from here to some other climate, and that transition may be triggered by the changes in AMOC. Okay. And this is what the IPCC report now highlights. There are many things here which are tipping point, not one. Okay, I only highlighted this because that was one which was well documented. There are many other things which can tip on Earth. Okay, now then people ask me, can you predict the tipping point occurring at some temperature rise? No, we cannot do that simply. But the major new concern is not about tipping of any one of these. It's called the cascade of tipping points. One tipping point occurs, that is the AMOC, it can trigger other things to tip also. So the Earth climate system is very, very delicate and very nicely balanced. If you upset one part, it may upset other parts. So that is the point people are highlighting now, that there are cascade of tipping points which can be triggered by this particular tipping point of that Atlantic circulation. So they are connected in some way. So this was warning given even 3 years back. Now, in a recent paper, they are indicated which are the ones which may cause problem when you are having 1 to 2 degrees change, which is chances are very high it will happen. Okay, they have identified various points in the Earth where tipping can occur. Okay, catalog of abrupt shifts in the climate models. Okay? And there are already, fortunately, monsoon doesn't come in that list, but there are many other things which can start changing in this case. Okay. So Tim Lenton, a leader in this area, he has a nice chapter in a book, very nice book. I recommend this book strongly. The Future of the World's Climate by Sellers and McPhee, published 20 years ago, but still relevant. There's a chapter in where Tim Lenton has looked at climate subrests due to tipping points. Okay, very nice article. And the key point I want to highlight, which is that the tipping points are not things which have high probability occurrence. Probability occurrence is pretty low. Okay, so people say it's all right, 1 or 2%, 3%, but impact is very, very high. It alters the Earth's climate so dramatically that we need to worry about a low probability event because of its high impact. This product is more important. Most of the time, the focus has been on even with high probability and low impact, which is important. For example, heat waves, extreme rainfall events, those are all much higher probability events. But I would say the impact is local and regional. But these are ones which have global impact and catastrophic impact. That's why I think we should think about it. Okay, so I'll conclude here. So I have some time. So what we have seen from the evidence is that Earth climate change can change rapidly, okay? And a cascade of tipping points can trigger rapid climate change. It's a low probability event, but high impact. And so when you look at 1.5 degree limit proposed in Paris, a lot of people ask, why are they making so much for the 1.5 and 2? It's merely to be more cautious, that's all. The difference 1.5 and 2 is not really large, but if you're a cautious person, you will try to limit to 1.5, not allow it to go to 2. So that is the spirit of that agreement. And a lot of people don't understand it. That the reason why I know a lot of people are skeptical is we're already at 1.3 today. Okay, so 1.5 is going to happen, unfortunately. But all people are saying is that take the action now as soon as possible. Don't wait for things to happen, because there are various surprises that are in the list. And remember, many of these are not well understood, and that's why I thought in this audience I should talk about it, because there's plenty of scope for research and exploration in the area, because this is not an area which has been fully understood so far. And I want to conclude with one moral story about the ozone hole. All of you know these three people got Nobel Prize in 1995 for highlighting the fact that ozone has been occurring. Now, this happened when I was doing my graduate studies in US, and these people wrote papers in the 70s talking about slow decline of ozone, 1 or 2% decline, 3% decline. That's all they talked about. Why? Because I remember that because some of my work was not related to it, but connected to it, because their prediction depended on accurate reaction rate of various reactions. Okay, and at that time, I remember that the reaction rate were not known accurate to a factor of 10. That was the inaccuracy in the data at that time. Okay, and so when this was published, people said, "Yeah, I know, but your data is so inaccurate, we'll not worry about it." But they continued to warn these people, and what happened was much worse than the warning. Okay, what happened was, in a matter of a few years in Antarctica, which nobody predicted, the Nobel laureates only predicted slow decrease in ozone in places where the CFCs are released, not in Antarctica. They didn't expect that. So it happened in a place completely unexpected where no human beings were living, and it occurred dramatically. Okay? And that's why it was called an ozone hole, because there was dramatic change. And it increased remarkably. See, in the 70s, it was decreasing slowly. But then in the 80s, just came down like anything. So this is a warning that ozone hole was not predicted. The hint was given by some scientists. Even that was ignored. I remember that kind of argument over there saying that this could be natural variation, it could be something else. All kinds of arguments are given until this thing fell on us. Okay, so a similar thing can happen with climate. So that is the warning I think I want to end on. And of course, this book, all of you will hear about it from Saravanan, a very nice book. And of course, I would recommend another book by Manabe. Both these are books which are worth reading as an introduction to climate modeling. Thank you.
For a wonderful lecture, such a comprehensive overview. I think even for many of us as outsiders, he conveyed that in a very compelling way. So now I don't know who is chairing. Rama, maybe.
Yeah. So since we are into tea time, shall we take only a few questions, or how do we want to do it?
I think 11:30 is tea time, right?
11.
Oh.
Okay, 11 is tea time.
Oh.
It doesn't matter.
I'm sorry.
Yeah,
and
so
beyond, okay.
questions, Spenta. I request all of you to wait for the mic because otherwise the online people can't hear the questions.
Hello, hi. This was fantastic talk. Thank you very much. One thing that occurred to me during your talk was what is the effect of microbes actually and living organisms in the oceans to climate change?
I can't hear him. I can't hear you.
What's the effect of microbes and living organisms in the oceans?
Yeah, that's a broad question. And let me tell you, since you asked question, let me pose this point. Nobody has, and I asked many people, the amount of oxygen on Earth has remained constant for the last 300 million years. We don't have a model as to why, because these microbes produce oxygen, okay? All these organisms in the ocean, they produce oxygen, and oxygen is maintained constant by them, and we are abusing the ocean, putting plastics and so on. Nobody has, I asked somebody, is there a model showing how the microorganisms maintain oxygen level on the Earth? Is not there. I think there's a big gap in our knowledge. And I'm telling you why I'm saying this. In the case of fossil fuel emission, burning fossil fuels, carbon dioxide has gone up dramatically by more than 100 ppm. One can show that oxygen has gone down by 100 ppm. One can show that because it does, chemical equation is there, it has to go down. It has been measured very nicely. But how the oxygen is maintained constant by the microbes, I have not seen, I may be ignorant, but if anybody sees, please let me know. I have not seen a model for the, how, and at this point was raised by the famous scientist Lovelock. He pointed out, that's why he had this Gaia hypothesis, that Earth maintains its status. And his argument is there are many things going on which you don't understand, which maintains homeostasis, temperature and concentration of oxygen especially. Oxygen concentration maintenance is the biggest mystery we have. Remember, oxygen is not a natural component of the Earth's climate. It is not. And it has been constant for 200 billion years. And nobody knows. And I don't know why, maybe it's difficult to do research on it, but this is, I know a few people in earth sciences who know something about it. Maybe you should ask them to come and give a talk here. I don't know.
So there are no models.
Huh?
So there are no models which couple photosynthesis with carbon dioxide, etc.
Yes, I mean, let me tell you, big people, there are earth scientists who are looking at it. I know there's one professor I can ask him to come and give a talk. But they can't tell you what happened in the last few million years. They look at the whole 4 billion years Earth cycle. Yeah, they have looked at it. But I want to talk about with measurement. I'm talking about the concern I have is the kind of pollution we're dumping on the ocean, plastic and so on. And nobody, as a matter of fact, I want to make this comment that today the irony is because of Hubble Space Telescope and other things, we know much more about the universe than about the Earth. Okay, this is a mystery. I mean, I'm always amazed. Our ocean floor is not completely mapped. Moon is totally mapped. Mars is totally mapped, but our ocean floor is not mapped. So this is interesting that we look up to the sky and not look down. I can tell you, I'm sure many of my colleagues will agree. It is very difficult to get a lot of funding for earth sciences. It's much more easy to get funding for watching the universe. Because, I mean, I don't blame anyone. It's a human curiosity drives us to understand how the universe started. So James Webb Telescope gets what, $100 billion, right? We can get it for, if you want money, you won't get it. So that is a mystery that to understand our own Earth, we are not getting sufficient money, but we are willing to spend money understanding the universe. That is human nature.
Hello. So carbon dioxide, of course, is one of the main anthropogenic interventions.
Yes.
But I also read or hear about the effect of pollutants and sometimes even like the blackening of which has an opposite effect.
Okay. I will not spend too much time on it because there's some politics around it, which I got to go and involve.
Okay.
Yes, soot has a local impact, not global. Okay, but it was made into global for political reasons. And George Bush, President of the United States, was part of that. See, if you remember the political history of climate change, Al Gore was a great believer and a great person in terms. So he wanted to be part of the Kyoto Protocol, but he lost the election. Okay, and then Bush came, and Bush made a public comment that I want to be part of it because black carbon is very important. Completely wrong, totally wrong. It is important locally, yes. There are parts of Himalayas due to soot are having glade melting rapidly, but it's not a global issue. The global issue is carbon dioxide, methane, other gases.
But
aerosol is very local. Huh?
Yeah, so sulfur dioxide, all the other emissions.
Yeah, but they're all local. I can tell tomorrow you have two speakers, they'll say more. But the interesting part is sulfur dioxide dominates over black carbon, factor of 10 more, okay? And as a matter of fact, as I didn't have time, we are not warmed up by more than 1.3 only because we have put up SO2 also. So the CO2 should have warmed it by up to 2 degrees. So 0.7 cooling is done by SO2, and that will go away now because air pollution control in Europe and also in China, and I hope in India, if it occurs, that will come down, then we are in trouble.
So
that's the problem. So soot is a distraction to me. Anyway, tomorrow Chandra will talk about it. You can hear from her because we may not agree on all these issues. So soot to me was mainly a local issue, which was made a global issue for political reasons. That's my view.
Sulfur dioxide, you are saying, is it will only as we control sulfur dioxide.
Yeah, the key point why to me aerosol is not as critical as CO2. Aerosol lifetime is 1 week. I can stop it tomorrow if I want to, right? And I think we should do it because I suffer from asthma. I can tell you, in this weather, I have all kinds of problems. I was not sure I will complete my lecture. So aerosol is a very important issue in India. 1 million people die every year. Okay. And during the recent COVID, and how many of you know, COVID and air pollution combined dramatically to kill old people. So it's a very important issue for India. We should tackle it, but let's not mix it up with global issue, which is CO2 and methane. So I think we should keep these two issues separate. But you know, people made it into, they call it co-benefits, and they told us, you reduce soot and it'll help. These are two different issues. One is local, one is global. And one has appealed to it in different ways.
So we have a question from Kripa Gauri Shankar online. She says, like thermohaline circulation, what are the other processes of mass and heat exchange between the hemispheres?
I am not aware of any. This is the major exchange mechanism. Atmosphere also exchanges heat in the two hemispheres. So the heat is transported from south to north, both by from equator to poles, both the atmosphere and ocean. But in the case of this climate change phenomena, the ocean is more important.
Okay. Other questions? Sandeep?
So my question was that you say that there's a 1 to 2% chance that we.
I can't hear without a mask.
Yeah, no, you said that there's a 1 to 2% chance that we can approach this tipping point quickly. There's a cascading effect. Right now, are the Earth system models sophisticated enough to actually capture this cascading effect, how it might happen, various sample paths, come up with this 1 to 2% probability? You know?
Not very good. I can also talk about it. I don't think our models are good enough to really predict very accurately. And now, right now, there are many models. Not all models agree on when this will decline. If you look at IPCC report, there's a whole range of hundreds of years differences there.
But they're not even suggesting cascading effect. And they at least in the model suggest that maybe cascading can happen and you know what direction it might take.
That is a very recent paper. I don't know. Nobody has, I don't think. Have you seen anything? I have not seen anything. Yeah, in a complex model, I don't think anybody has.
So, Shaurendu had raised his hand. Shaurendu, would you like to unmute yourself and ask the question? Shaurendu? Okay, so maybe.
We have 15 minutes and then Professor Divecha, so maybe one last question.
Yeah, Rajeshi.
We're going to miss a tea break.
Hello. Yeah, you mentioned tipping points and the cascades that connect the tipping points. Are they connected in a one directions or can they go the other way around?
And what is, I can't hear you.
Sorry.
Can you take off your mask and
Yeah.
say it?
Hello.
Ah,
Yeah, you mentioned tipping point and the cascades that connect the tipping points.
Yeah.
Are the cascades in a single way or are they connected in both directions?
let me tell you, that paper is only a suggestion. There is nothing, no details there. You
Okay.
can go look it up. People are just making hypotheses. Nobody has any idea
Okay.
how one will affect the other. I can tell you that experience with Earth system, everything affects everything. There is no one-way process. There is always a two-way process. I'm not aware of any thing in the Earth's climate which is only one way. So I think it will go both ways. One will affect that, and maybe that will come back with some other effect.
Okay, let's break for a quick tea and come back on time, please, for Navroz Dubash's lecture.
11:30. Sorry for
Yeah.
that. Thank you.